So we're going to take a look at the idea of zero knowledge proofs, and then tossing a coin with no actual coin to toss. So a zero knowledge proof is a situation where we need to convince someone that we know a secret without actually telling them that secret. So let's say I have some information that would be beneficial to you, and you're willing to pay for that information, but only if you can be convinced that I actually know the information. So you don't want to pay for something and then I not actually know it, and I don't want to tell you the secret too soon. I don't want to give it away, because if I give it away, then you have it and you're not going to pay for it. So how can I convince you that I have that information without telling you what that secret actually is? In This idea of zero knowledge has been around since at least the mid-1980s. And in 1990, there was a paper published that involved zero knowledge protocol. The title was involved something like zero knowledge protocols for children, or teaching your children about zero knowledge protocols. Anyway, the idea was there was a cave scenario given. And the idea is that you can come into the cave and go down the left corridor or the right corridor, and at the back part of the cave there was a wall. But the wall would open up if you knew the magic word. And so you could come in and go to the left, and if you knew the magic word, come on through and then come back out the other way, or go the other direction. If you know the magic word, come through. If you don't know the magic word, when you get to the wall, the only option is to turn around and come back out. And so if I know the magic word and want to convince you that I know the magic word, but I don't want to give you the magic word, I don't want you to know it, I just want you to know that I know it, then we could do a test. So we could both come together, say, to the cross point out here. We don't want to go all the way back to the wall, because then I have to say the magic word in front of you and then you know what it is. So you wait here, and then I go one of the directions. Either I go to the left, back to the wall, or to the right, back to the wall. You flip a coin that tells which direction you want me to come out. If you want me to come back out on the left side, you want me to come back out on the right side. And so I go back there. If I say had gone to the left and you want me to come out the other side, then the only way for me to do that is if I know the magic word and can come through the wall. If I had gone the other way and you wanted me to come back out that same direction, well, anybody can do that, right? I could go to the right, go to the wall, turn back around and come back out. So you won't gain any knowledge about whether I know the word or not if I do that. But otherwise, if I go to the left and then come back out on the right-hand side, then you might be convinced that I do, in fact, know the word. Some scenarios we might have to do this multiple times. You get more and more convinced the more and more I can repeat it. But we can have this scenario of zero knowledge, in that you still don't know the magic word, but now you can be convinced that I actually do know that word. And so the components of zero knowledge proofs are, first of all, completeness. That if the statement is true, then you can be convinced, you will be convinced by someone who is honestly following, somebody who honestly knows the secret will be able to convince you that they do know the secret. Another aspect of zero knowledge is soundness. If the statement is actually false, let's say I don't really know the password, then even if I'm trying to cheat, then you're not going to be convinced. Now, there's a slight possibility, a slight probability that I can be lucky enough in terms of my cheating, that maybe you just always happen to, when you toss the coin, guess or select the way that I had already guessed, and could be able to sneak around somehow and come back out the right way and always somehow cheating to get away with it. But the more often we did this, then the less likely that my cheating, my lucky guesses would work. And so if I really don't know the password, then you're going to find me out. And then again, the zero knowledge aspect of that is if the statement is true, the only information you gain is that the statement is actually true. You don't learn anything else from that. So if it's true, then you can be convinced. If if it's false, then no matter how hard I try to cheat, you're not going to believe me. And the zero knowledge, if it is true, then I have convinced you of that with the completeness aspect, but you don't learn anything else other than that the statement is in fact a true statement. So we're going to take the same kind of idea and look at tossing a coin. So we're going to toss a coin, and the idea is that we don't actually have the coin, so we're going to try to toss the coin or mimic the result of tossing a coin without actually having that coin available. Again, we're not going to worry about writing a program to do this or anything like that because maybe you still wouldn't trust the program. I wrote the program and you think that my program cheated somehow or whatever. And so if we both think, say I think I'm the one that's tossing the coin, so I think heads or tails, and I keep that to myself, and then ask you what it was, what you call, then I could always just say the opposite. If I thought heads and you said, yeah, I'm calling heads, I could say, oh no, I was thinking tails. And so I would easily be able to cheat if I was just trying to keep that in mind. If I announced it ahead of time, okay, the toss was heads, then you're obviously going to say, if you want to win, you will say, hey, heads. And so that doesn't work. It also doesn't work for us to both try to say it at the same time. Here's what the toss is. I say heads or tails, and you say your guess at the same time, because one of us could delay just enough to hear the first part of the letter that the other one is saying and be able to change our answer to match that. Some people are better at that kind of saying what somebody else was saying or the opposite of what they were saying right after them and make it look like or almost sound like they were at the same time. But that's cheating as well. And so I could write heads or tails on a piece of paper and then have you guess and then show you the piece of paper. But if I'm really good at sleight of hand, I could have heads written on one piece and tails written on another piece, and you not notice that it's written on both. And when you say whatever your guess is, I could show you the other one and say, oh no, sorry, you lost. So what we need in this situation is we need something that we can both trust. So one thing that we can both trust and not be able to cheat would be if we had a third party that was completely trustworthy, then that third party could take care of the keeping the information and sharing it and so on. But if we don't have that third party, or there's no third party that we can both trust, then that doesn't work either. So we're going to very briefly describe a mathematical way that will allow us to mimic a coin toss without giving any information away until the very end, and then actually come very close to being a fair simulation of an actual coin toss. So to do this, we need a bit of maths. We are going to talk about integers only in this, and actually we're going to be talking about just positive integers. And so with a and b being integers, we say that a divides b if there's some number so that a times c is equal to b. In other words, if a is a factor of b, we say that a divides b. A goes into B. Normally in the maths literature, this is written with a vertical bar, so A bar B is read again as A divides B. So 5 divides 10 because 5 times 2 is 10, and so there is this integer C. 10 does not divide 15 because there is no integer, so that 10 times C is equal to 15. If A and B have no common factors other than 1, we say that A and B are relatively prime. Neither number has to be a prime number itself, so 9 and 10 are relatively prime because they don't share any common factors other than 1. Sometimes we would say 9 is relatively prime to 10, or 10 is relatively prime to 9, or we say they're relatively prime with each other. with with a number, an integer, say a positive integer that's bigger than 1, we can think about these numbers as kind of wrapping around in a sense. And so this wrapping around is what we mean by integers modulo of the number n. So maybe say mod n. So think of like a 12-hour analog clock. When it gets to 12, I guess a digital clock the same way, right? When it gets to 12, it wraps back around. It starts back at 0. And so the next hour from 12 goes back, then goes to 1 and 2 and 3 and gets back to 12 and wraps back around again and again. And the same thing happens, say with a 24-hour clock, except the wrap happens at 24 rather than at 12. So if the time on a 12-hour clock is 10 o'clock and we say, okay, what time will it be 5 hours from now? Then that would be 3 o'clock rather than 15 o'clock. And so on a 24-hour clock, it would be 15, but then the wrap would happen just at a different time. It would happen at the 24-hour time rather than at the 12, the wrapping at 12. So this modulo n situation is with integers usually written with something like a z mod n, which is z with a subscript. And so z mod 6 is the set of numbers 0, 1, 2, 3, 4, and 5. And 6 wraps back around to 0, and it keeps going. So 7, 8, 9, these are represented with the values from 0, 1, 2, 3, 4, and 5. The arithmetic in z mod 6 is a little bit different than what we tend to think of. The arithmetic, 1 plus 2 would still be 3. That's normal. That's the expectation. But 3 plus 4, because of the wraparound, 3 plus 4 would correspond to 1. We can also go the other direction. So negative 1, going from 0, going the opposite direction. Negative 1 would get us back to 5. Negative 2 would be 4, and so on. 2 times 5, which is 10, but with the wrap, 2 times 5 is 4 in this universe. 5 times 5 is 1. And 2 times 3 is 0. Now notice that with normal numbers, the way we're used to thinking, that if you get 0 as the answer, then you have to have one or the other of those numbers, at least one of them, has to be 0. But in this world, 2 times 3, neither of which is 0, multiply those together, you get 0. Now typically when we're doing this, we don't use a regular equal sign. We normally use 3 lines instead of just the 2. And we would say something like 3 plus 4 is congruent to 1 mod 6. Equals is okay for a lot of scenarios in terms of the applications and how this is used, but being a little more precise, we should say congruent to. All right, so in that world of things, in this z mod n, if we look at z mod n star, what that means is everything in z mod n that is relatively prime to n. So in z mod 6, we had 0, 1, 2, 3, 4, and 5. 0 doesn't share that common factor of 1. We're only talking about positive integers, so we're going to leave that one out. 2 and 3 and 4 both share factors with 6. So the only things left in z mod n or z mod 6 star are 1 and 5. For z mod 7 star, it's 1, 2, 3, 4, 5, and 6. Z mod 10 star, we have the even numbers are ruled out and the 5 is left out because of the common factor. So in that case, we would have 1, 3, 7, and 9. Turns out that every number in z mod n star has a multiplicative inverse. In other words, a number that you can multiply by that number and get 1. In z mod 10 star, we have 1 times 1 is 1. That's not a surprise. But 3 times 7 and 7 times 3, which are both 21, also correspond to 1. So they're both equal to 1. And then 9 times 9 is also 1 in that world, because 9 times 9 is 81, and with the wrap, that gets back to 1. So these numbers all have inverses. Some numbers have another number that when you square it, you get that value. So for instance, In Z mod n star, we might have a number a that when you pick a different x, you square x, you get that value a. In that case, we say x is a square root of a mod n. So in the Z mod 6 star world, we have that 5 squared was 1, and so 5 is a square root of 1 in the mod 6 world. 1 is also a square root of 1, right? 1 squared is 1, 5 squared is 1 in that setting. We might be surprised by that until we remember that 5 was the same thing as -1 in that world, and so 1 squared is always 1, and -1 squared is 1. But some other things can also have square roots. But in this setting, we say that 1 then is a quadratic residue, mod 6. And 5, the other thing in that world, is a quadratic non-residue. It's something that doesn't have a square root. So residues have square roots, non-residues do not have square roots. So the things that are quadratic residues, the things that do have square roots, we're going to write as Qn. And if it doesn't have, we're going to write it as Qn complement. So the C there indicates that these are the things that don't have square roots. And so all of Z mod n star are the things that have square roots and the things that don't have square roots, but that are still relatively prime to the number n. So in terms of keeping track of things of being having square roots or not having square roots, there's a symbol called the Legendre symbol that is looks like division, but it's not division. And so it's written as a with p, and a with p is 0 if p divides a. In other words, if one of the factors of a is the number p, we get 0 out of this calculation. If a has a square root, then this calculation gives us 1. And if a does not have a square root, this calculation gives us -1. Now, we're not going to go into the details of how to do the calculation, but it's a straightforward set of calculations. Software can be written that will do this for us, other ways to do this kind of calculation. And it allows us to distinguish between the quadratic residues and the non-residues modulo some particular prime p. Turns out, though, that with a non-prime number, say n equals p times q, that this value of a with n is the value of a with p times the value of a with q. And so if you get 1 as the answer, it doesn't necessarily mean that a has a square root in the mod n world. You can get 1 out of this calculation if both of these, a with p and a with q, if both of those are -1, then the value is 1, and it turns out that in that setting, a just looks like it has a square root. It doesn't actually have a square root. And so what we get is the numbers where that value a with n being 1, some of those are quadratic residues. They actually do have square roots. And some of those are quadratic, well, they're called pseudo-squares. They look like they have a square root by looking at just that one value, but it turns out that behind the scenes, there's not really a square root in there for them. And so without the extra information, it becomes difficult to tell whether something actually has a square root or whether it's a pseudo-square. The only way to be able to tell is if you actually know the p and the q, and then you can do that calculation. But otherwise, just knowing that a with n is equal to 1 doesn't tell you whether the number really is a square or whether it's a pseudo-square. And so for the coin toss algorithm that we're going to describe briefly, we have Alice is going to select 2 distinct large prime numbers p and q and calculate the value p times q. So this is the n. She's then going to select an x so that x with n is equal to 1. By the way, in cryptography, it's always, this tradition is that Alice and Bob are communicating. And so in this case, Alice is the one flipping the coin. So Alice picks these two primes P and Q, calculates the n, and selects this n, selects this x so that x with n is 1. And if she wants the toss to be heads, then she chooses x to actually be a quadratic residue. She chooses an x that actually has a square root. If she wants the toss to be tails, then she's going to select a pseudo square from this. Now, from her perspective, because she knows P and Q, this is an easy calculation to make. This is something that she can easily do. But now she sends the n and the x to Bob, and Bob can't do the calculation. Bob can't calculate anything about x to know whether x is actually a quadratic residue or whether it's a pseudo square. And so all Bob can do is make the guess. Hey, I think it is a quadratic residue, or I think it's a pseudo square. In other words, Bob says heads or tails. The coin has already been flipped. The decision has already been made. Once the n is selected and once the x is selected, the decision of heads or tails is already determined, and Alice can't change that. But by telling Bob n and x, she hasn't told him what that flip is. And Bob can't do the calculation without knowing P and Q, because it just turns out that this calculation would exceed the time limit, maybe in some cases, of the universe. We don't have a good algorithm for factoring. There might be one, but no one knows one. And so with what we know at this point, Bob can't determine the actual answer without knowing P and Q. But once Bob is on record with the choice of heads or tails, then Alice goes ahead and sends the values of P and Q to Bob. Bob can then calculate x with P. If that happens to be -1, then that means that the toss was tails. If x with P is +1, that means the toss was heads. And everyone then knows whether the choice was heads, whether it was tails, and whether Bob was correct in that choice. So we're able to toss the coin and not only not share what the toss was, but commit to that. So it's a little bit more than what we asked for in the zero knowledge proof, that Alice is committed to that. She has the secret, she knows the secret, and she can convince Bob that she knows that secret. And at the end, we have the coin toss. It's fair. Neither side can cheat. And we did that without having a coin at all. So if you have questions, let me know in the comments, on Discord, wherever, and I hope you have a great day.